Oh, click. All right, excellent. So we are continuing to work our way away from the Earth. We started out at the Earth. We talked about how it's tilted. We talked about its orbit. We then moved out to satellites. We talked about what it meant to be weightless. The astronauts falling, continuously falling. And then we got ourselves out to the moon. Talked about what we see, the phases of the moon. And then ultimately we talked a little bit about the eclipse, obviously. So now let's keep moving out to the next larger objects that we encounter, and that's all of the planets, the solar system itself. Now, I didn't put this in my note. It is in the textbook. I don't have a question on it per se on the test, but let's just talk a little bit about how the solar system comes about. How did our solar system and our planets form? Because you may already know that in the solar system, all the planets seem to head in the same direction. They all go around the same way. They don't like some go clockwise and the other counterclockwise, and it's a chaotic mishmash of things. Everybody's kind of heading in the same direction. Now, we haven't talked about stars and the life and death of stars, but we will. But in this region of space where we exist, billions of years ago, there was a really big star, what we call a first generation star, that ended up exploding in what is called, do we know what that exploding star is called? If we see that in space. We're going to talk about this in the next couple lessons. Yeah? No, we're going to talk about neutron stars, but that's not what this is. Supernova, have you ever heard of a supernova? Anyway, it's when a star explodes. We'll talk about why that happens. But there was a star in this area that exploded, and all of its elements that were formed in that star spread out into space. And then gravity kicks in. Eventually, even though it's got pushed away by an explosion, gravity is going to start to pull those little pieces back in, okay? And what happens is there's still a lot of hydrogen in these kind of dusty, dirty clouds in space. And as gravity pulls them in, if there's any little bit of rotation in that dust cloud, as gravity pulls it in, everything starts to spin faster. Figure skaters. Figure skaters, excellent. I like to make fun of figure skaters. Excellent. Don't worry, hockey players. We got the up on them. But anyway, figure skaters. Figure skaters, you get yourself in the groove and you do one of those spinny things. I don't even know what it's called. Spinny thing. Spinny thing. Okay, a spin. All right. And then you bring your arms in as you spin. What happens to the spin? You spin faster, okay? That's called the conservation of angular momentum. What an awesome law of physics. It means that if you bring things in that are spinning closer to the center of the spinning axis, it has to spin faster. I'm not going to explain why it is, but it does. So, as the dust starts to come together to form a large center ball that eventually is going to become our sun, it starts to spin faster, and everything starts to spin in the same direction, okay? Out past that inner ball, which becomes our sun, there will be some other bigger rocks that start to collect their own stuff around them. They become the planets. They also condense their spinning energy. So yes, everything spins the same way, but also those little planets, as they start to form, they spin on their axis because of the same spinning energy. So that's why in our solar system, everything heads in the same direction. And as the planets are being formed by gravity, they start to rotate in the same direction because they're conserving their angular momentum. All right? You may have heard of momentum before. Momentum can be used to describe many things. In hockey, right? We say, oh, big momentum swing. We killed off that penalty and now we've got the flow of the game. Momentum in physics is like that. Cars that are traveling along, they don't want to stop. Why? They're carrying momentum. You got to take that momentum out of them. Spinning things don't want to stop spinning because they're carrying momentum. So as everything spins in the same direction, it's got that same directional momentum. And as the planets are formed, they spin in the same direction because they're carrying that same momentum with them. Yes? Yeah, that's a question mark. That's what's gone on there. Something has happened to that. So we could talk about that. Yes? No, retrograde motion is from our perception of the planets on Earth. Because we're on a moving frame of reference, it looks as if some of the planets go backwards in the sky once in a while, and it's because we're passing them. It would be kind of like if you're in a car, right, and someone was driving kind of at you. If they were on a curve, you would maybe see them kind of go back because you're both moving. It has to do with the frame of reference which you see it. So no, that's not retrograde motion. You're right, retrograde means to go reverse, but that's a different scenario. Okay, so that's how our solar system is formed. Let's then go over some of the information. All right, so you've already got the title solar system, probably don't need to write that down. Again, I tried to squeeze this down into as few words as I could, because again, we don't like the blah, blah, blah of our notes. We want to just get the bits of information in our brains so that we can write it out on a test. We can always fill in the extra words to make it sound good when we write our answers on tests. So the solar system, the sun, 8 planets, and of course everybody wants to fight for poor Pluto. We'll talk about that at the end. And their moons. And again, the planets revolve around the sun. And we break them into 2 groups, the inner planets and the outer planets, and that's because of their properties. In my note, I don't talk about the asteroid belt, but in between the inner and outer planets, we do have the asteroid belt. I can't spell asteroid. A-S-T? See, I want to put asteroid. That's the way I'm sounding that out. How is it? A-S-T, oid belt. All right. The asteroid belt is essentially a failed planet because of the pull of the other planets, keeping that stuff from coming together. Yep.
Do all the planets' moons look the same? Like, are they all made of the same stuff?
Good question. Let's go with a not necessarily. Yeah, that's a crappy teacher answer. You're right. You're right. I'd have to think of we'd have to talk about the origins of those moons. If the moons, because the moons are forming just like the planets formed, right? Now, holy moly. Let me get through some stuff, and then I'll try to answer that. I don't have a good answer for that right now, but I'm going to think of one. Yep. Yep. I'm giving you the theory that I was taught in my astronomy course. It's the Nebula Theory of that. You have other theories that you know of? Well, what do you have?
Well, there's ones that, well, yours is like the Big Bang Theory.
Yeah. No.
Yeah.
No. The explosion is not the Big Bang. It's not. That's not what I'm talking about.
Okay, well, there's the Big Bang Theory.
But that's the origin of the universe, not necessarily the origin of our solar system.
And then there's the one that, like, God created.
So we're talking then about a creationist theory. Okay. So I am going to go with the science-backed theory that I was taught in university. To say that that is correct versus a creationist theory, this is an interesting debate. I'm never ever going to get done this lesson. To say that my theory is correct over the creationist theory, that's interesting. I'm gonna give this about 2 minutes, 3 minutes of discussion. In the 1500s, let's go earlier, 1300s, etc., the church was a very, very powerful thing. It's a very powerful thing right now, right? The Pope. I'm talking about the Catholic Church. Who's kidding who? I'm talking about Christianity and the Catholic Church. You know, the Pope can say a thing, and many people on this earth who follow the Pope and the Christian beliefs will then act on that. That makes them a very powerful person. So back in the 1500s. Who had it first? Copernicus. All right. There was a scientist called Copernicus, and he before our knowledge of the solar system now, they believed that Earth was the center of the universe, the entire universe. The Earth was the center. And then based on observations of various things in the sky, and on a theory, Copernicus said, you know what? We can explain the universe much better if we put the sun at the center of the universe. They didn't know anything about gravity at the time, so they kind of put that idea out there. But so Copernicus then got into big trouble from the Pope, because the Pope said, no, the Earth is the most important place because humans are created by God, and therefore the Earth is super important. And so, no, you're wrong. The Earth is the center of the universe. And because Copernicus was scared, he said, sorry, you're right. I was wrong. Okay, so then comes a couple of other guys. One guy by the name of Kepler, Johannes Kepler. He determined that those rules of orbital motion. He figured that out. Then Galileo. Galileo took a telescope and looked at Jupiter and saw the moons going around Jupiter. And he said, hey, if the moons go around Jupiter like that, then why the heck can't the planets go around the sun? If we see a little mini solar system out there, why doesn't it work that way? So then he wrote a big thing. I think the sun's the center. Again, the Pope comes along. No, Galileo, you're wrong. Okay. So then in the end, the church said, Galileo, you're wrong. And he said, well, I'm saying what I'm saying. It's the way it is. Eventually, and in actual fact, this was in the early 2000s. I think it was around 2002. I think it was Pope John Paul II. He finally said in an official doctrine, sorry, Galileo, you were right. The sun is the center of the universe. Okay, not the universe, but our solar system. Okay, so in this day and age that we live, not necessarily the Pope, but there are religious believers, and my uncle's a priest, and I've had this discussion with him, that we can still talk about origins of the universe. We can still talk about the Big Bang Theory. We can still talk about origins of the solar system and not be against what a church says. Again, I've discussed this with my uncle. We're going to talk about the Big Bang Theory. We're going to talk about that. The question then can become, well, who started the Big Bang? What started the bang? All right? And some religious scholars will then say, that's where we can put God. God maybe started the bang. All right? So even though it doesn't necessarily follow the creationist theory that you might read in a Bible, in science, I believe, is starting to work together, not too badly with religion, to say, well, this is what we're seeing. It doesn't mean we're excluding a spiritual entity from the entire thing, but we're putting it in a different place than maybe the way the Bible says. Anyway, that's my particular view and my view on it. All right, you know, I'm a Christian. I'm a Catholic, so I've had to, as I've learned science, I've had to kind of go through and reevaluate where I do that. So that's a great question. So I'm giving you what I've learned that I've reconciled with the way I think of things. All right, and that doesn't just say that your opinion isn't valid if you have those opinions on creationism, but we do in the world of science base our theories on what we observe. So I'm going with our observed knowledge. Is that an answer that you're looking for? Is that okay? Yeah? Okay, awesome. All right, okay. And it's a great question. It is a great question. So that particular one, and I'm going to put them down short because I took way too much time here. Yes? I know, I knew it was way too long. As I started to tell it, I thought there's no way I can make that short. Okay, so don't worry about writing this down. You can see here Mercury, Venus, Earth, Mars. We call these the terrestrial planets. Then we have the asteroid belt. There's some other larger objects in there. And then Jupiter, Saturn, Uranus, Neptune, and then Pluto again is out there because it can kind of cut in between. And then we've got some other types of objects way out there, and I'm not worried about that stuff right now. Okay, so let's talk about distances when we talk about stars. Good questions. Crush my lesson. That's okay. We'll just go a lot faster. Come on, people. Write with the swiftest of pens. Yes.
People said that the moon was created because something hit the Earth.
Yes, correct. Yeah, that's the current view that I've taught, that I was taught, right? Astronomy is one of these interesting subjects where we're learning more and more about certain things every day. But it tends to be the things that are very far away from the Earth that we're learning a lot about because we've got these awesome telescopes now, right? So we're learning things about planets around other stars, right? We're learning things about Earth-like planets. Could there be life out there? That'll be our aliens discussion later on, right? But the moon they've studied pretty closely, and you're right. They think that the moon was a large asteroid that collided with the Earth, all right, and blew a chunk off of the Earth along with this asteroid, which then went out into space because it had energy and speed, but then got trapped and everything kind of condensed in because of gravity and moved around. Yes? Well, and there's a lot of Earth-like minerals on the moon. Correct. Yes? The easiest answer is gravity. All right? And I'll talk about that in a moment. So, how do we measure distances in the solar system? We could do it with meters, but we would have millions and millions of meters, 10 to the 6, 10 to the 7, over and over again. So scientists have defined a special unit. We call it 1 astronomical unit. It is essentially the average distance from the sun to the Earth. So we call that 1 AU. It allows us to compare everything to the Earth. So our Earth then is 1 astronomical unit from the sun, 1 AU. So when we start to compare other planets, we can then look at how close they are. Are they half an AU or are they 2 AU, etc., etc. And it is 1.5 times 10 to the 8 meters. All right, the inner planets. So we're going to start at the sun. We're going to work our way out. Yes?
Planets get bigger as they get further away from the sun, right?
The inner planets tend to be smaller, and the outer planets tend to be larger. I'm sure I've learned a reason for that at one point in time in my life, but I can't remember it right now. So they're similar to Earth. They're small and rocky. Now, at this point, and I still am going to do it this way. I might not get done. Who knows what's going to happen in the world. Click. At this point, I want you to write down these bullets, but don't write down what's in the box. And at the very end of my note, there's a chart. And if you've got the note on your device, scroll to the end and you'll see a chart. And the chart has all the information about the planets, like how far it is, and how long it takes them to go around an orbit. In other words, how long is its year? How long does it take to revolve or rotate on its axis? How long is its day? I don't expect you to memorize that information. But to me, that's handy information just to think about as we try to imagine the planets. So Mercury is fairly small, and it is close. And it is hot, because it's really close. Now, at nighttime, it's super cold, because when you're pointed away from the sun and there's no sun right on it, and there's no atmosphere to keep the heat in, it loses all that heat that it gained, and it gets pretty cold. It doesn't have any moons, rings, or atmosphere. Did anybody spot that chart? Now, if we take a look at the chart, and I'm just going to quickly escape out of the PowerPoint, and I'm going to do a little cheat move here. I'm going to roll down to here, and I'm going to click on there, and I'm going to come back in. You can see here for Mercury, the distance from the sun, 0.39 AU. That's close. It's like 1/3 of the way. It's close. Its rotational period in Earth days, it only takes 58 days to get around once. That's a year, 58 days. Remember when we talked about satellites in orbit? What happens when that satellite gets really close to the center of, or as it gets close to the surface? It gets fast, right? I was playing with that. It gets really fast. So the closer you are, in terms of the energy well, you're further into the energy well, and it goes around like crazy. So Mercury goes around like crazy. Another interesting one is the tilt. Do we have the tilt? The inclination, 0 degrees, straight up and down. There is no tilt to Mercury. Okay? All right. Yep. How do you measure the tilt? I'm going to go back here so that we can write Venus. How do you measure the tilt? Again, with a telescope. That's the way it would have been done originally. Ultimately, maybe sending a satellite to that, all right? You can visually see that rotation. And so we create a flat plane. We imagine a flat plane that's in where all of the planets go around, right? And then we see how does it rotate with respect to that plane. See what I mean? So if it's this one doesn't, this one's straight up and down. The Earth would be, 23 degrees like that, and it would rotate then as it goes around. There's a little bit of a tilt to it. It's not rotating perfectly in line with where it goes around. That's how they would measure it.
And how does it not get stuck to the sun?
Same reason as if we put a satellite far enough away from the Earth and it's not running into the atmosphere of the Earth just to take the energy away. It's not like pushing any molecules like air. Then it's going to keep that orbital motion, that momentum. It's just going to keep it. So it's still far enough away from the sun that it's not running into any particles that are coming off of the sun to slow it down. There's nothing in its way. Okay? Venus, second. Rotates in the opposite direction. Now, that means it doesn't follow that same rotation. It goes back the other way. That's one of those question marks. How did that happen? If it formed the way I said, they should all be spinning the same way, carrying that spinning motion. That's a good question. Was there a collision? Perhaps there was a collision at some point in time with a large object that then gave it its energy in the other direction and gave it a push and got it going the other way. So we think that there was a collision there. Okay? All right. It's super hot. It's super hot because it has pretty well only carbon dioxide in its atmosphere. Some scientists believe that Venus was much like the Earth and had a very little bit of carbon dioxide. And then, for some reason, it started to heat up, which changed the chemical composition of some of the rocks, which caused it to eject carbon dioxide into the atmosphere, which then acted as the greenhouse effect, which then made it hotter, which then affected the rocks, which then ejected more carbon dioxide, which then made it hotter, which then affected the rocks, which then ejected more. You see how this is working? We call that a positive feedback, where one change caused more of it to be ejected. This is what we call a runaway greenhouse effect. For those who don't believe that global warming is a thing and that carbon dioxide isn't bad, say, go to Venus, because that's what's going to happen if we were to put all of the carbon dioxide into the atmosphere. It would get super hot. Yes?
So it's getting hotter right now.
No, we believe that that reaction has stopped and it's ejected all of its carbon dioxide. We don't see a change in the carbon dioxide concentration. That, what I just told you, is a theory. That's what we believe resulted in this large carbon dioxide in the atmosphere. It's a theory. A lot of things are theories, right? Because we weren't around to actually see it, so we got to come up with an idea for it. Yes? Ah, my goodness. Never going to get done this class. How do you know it's carbon dioxide? Did I show you, when we were doing chemistry, the tube that I've zapped and it made it a certain color? Carbon dioxide does a similar thing, except we can't see the light that it gives off. It gives off what we would call is infrared radiation. It's heat light, okay? And when we take our telescopes and we catch some of that light that's coming from the atmosphere, and we break it apart into the colors of the rainbow using something like a prism, and we look at the different colors of light, they indicate to us carbon dioxide, because every compound and every atom has a special signature, a special light signature when we give it energy and we make it glow, like when I zapped it. Okay, so if I took carbon dioxide and I zapped it and I looked at the colors that were produced, I would get a signature for carbon dioxide. I can then take a telescope and take some of the light coming off of Venus. I can collect that with a telescope, run it through a prism, look at it, compare it, it would line up perfectly, and we'd say carbon dioxide. So we look at what we call the spectrum. It's called a spectral analysis. Yes? I'm going to click on this so I can keep going. Because we don't have time to stop. It would need water. It's 480 degrees Celsius. I'm going with death of the tree. I know what you're saying. I know what you're saying. Let's plant some trees and let's fix this place up. It'd be a nice place to visit once in a while if we could get some things growing. I'm all for it, but I think it's pretty hot. I'm thinking death of the tree. Yes? Do you mean how long did it take for that to grow, or will it ever decline?
How long did it take for this to go, like, how long?
To that runaway greenhouse effect? Like, are you worried that this might happen in the next couple of years? Is that what you're saying? Oh, okay. I don't remember. To be honest, I learned that, like I said, back in university. We could look it up. Right? Our star, our sun, is about 4.5 billion years old. So it had to happen between the start of our sun and now. So in the last 4.5 billion years, you see what I mean? I don't have a number for that. Don't ask me how we know it's 4.5 billion years old yet. Ask me that when we talk about stars. Yes. Nope, not playing that game today. Jess?
Where?
Are we writing as we're doing this? Because I want to keep going.
Hold on. On Mars, no wait. What's the planet that we travel to? Mars?
Mars, that's my next one.
Oh, never mind.
Okay, so we are the third planet. It's nice and comfortable here on Earth. Yeah, it can get a little cold and maybe a little warm, but usually it's around 15 degrees Celsius. So that's good. Why is it so comfortable here? Because of our atmosphere, all right? Our atmosphere catches the heat. So the sun comes in, warms our Earth. It then sends out heat light, which is called infrared, right? And our atmosphere catches it like a nice blanket, and it keeps us nice and warm. If we keep adding too much greenhouse gases, it's like we're putting on more blankets, and it's going to be warmer, right? That's really essentially it is. So the greenhouse effect is not bad. We need it. If we didn't have the greenhouse effect, if we didn't have the effect of the atmosphere catching that heat and sending it back down to us, we wouldn't be living here right now. So we need it. But it's the extra gases that cause what we would call global warming. Yes? That we wouldn't have that perfect conditions? Yes, it's true. Yes. If we were too close, we would be taking in more energy from the sun, because energy goes out in 3 dimensions, okay? So just like sound gets very quiet the further away you get. And that's because all the energy that comes out of my mouth here is spreading out in 3 dimensions, and that energy then gets spread very thin as it gets further and further away, okay? Light energy is the exact same thing. So if we were closer, we'd be being hit with a more intense amount of light that would heat the surface up more and increase the amount of energy that's in our little blanket system. And it could do things like, if the air gets too energized, it would have so much energy it might leave. It might have enough energy to get out of the bowl, right? Because molecules are doing the same thing. They're moving around. They're trying to get out of the bowl, right? Just like yesterday, right? They're doing the same thing. So if you give the molecules 11.1 kilometers per second energy, they're gone. They're not staying here on Earth. They're not gravitationally bound. So if we get too close, you bet the atmosphere is gone. It's burnt off. If we get too far, it's too cold. We don't have enough energy, and all of our water turns to ice, and life doesn't take hold, and we're not here. I love it. This is awesome. Have we wrote this down? Please write it down. Oh, Jewel, you want to crush my lessons. I'm recording all this. This is great. This is either going to go down as historically the worst discussion on creationism or the best. I like it. It's an excellent question. We are going to talk about, as we continue on, about galaxies, which contain billions and billions and billions and billions and billions and billions and billions, you get the idea, of stars, which you know, obviously, right? And we are going to talk about how in our universe, there are billions and billions and billions and billions of galaxies. We're getting to our aliens discussion too early is what we're doing. Which means if you take your billions and billions and billions and billions and billions of galaxies and multiply it by the billions and billions and billions and billions, you get something like 10 to the, 40, 50, 60, 70, 90, 10 to the 90, all these zeros, stars, which we now know that pretty well every star has about 5 planets. So that means we're dealing with vast numbers. And in the end, it's by chance where the big rock in the orbit was that forms that planet. But because there's billions and billions and billions and billions, it's like wanting to win the lottery and buying billions and billions and billions of tickets. You might win the lottery. So in the end, it's by chance that we happen to be in a solar system that resulted in a planet being in the perfect spot and resulting in life. Now, that doesn't mean that some creator didn't send the machine in motion to make that happen, because that could be the case. But in terms of science, it's by chance that we ended up in the right spot. What's that? It's a coincidence, correct. But can I continue with the slide? Because we're going to keep, even though we're just getting information, that's great. It's a coincidence. But that's not to say, and again, I don't want to discount any spiritual, being of some sort. That's not to say that machine wasn't built by that particular spiritual person that then resulted in that. Or maybe there isn't. And it is truly by chance. But that's what makes religion religion. You've got to make the jump of believing, right, that something put that into place. And then I guess that's our choice as human beings. We choose to believe that, or we choose not to believe that. But that's a good question. But that's what science tells me, that the numbers got us in the right part of the world.
Why was Mars the most studied planet? Why didn't
That's a good question. It's close. For us, it's the most convenient to get to. So when Earth gets close to the orbit of Mars, we're pretty close. So if you're going to send a spaceship out to land on something, Mars is a great great place to start. So, and it's really close, and it's very much like the Earth. Again, Venus and Mars they're in that edge of that, what we call the Goldilocks zone. That's what you were calling it, that perfect spot where Earth can have life on it, and the others are too far and too close. So it's nice and close. Yes.
What's the distance between Earth and Mars? What's the difference?
The difference, we would have to go and check our charts. Again, I'm looking at the time. It's a great question. If you were to go to that chart, you know what? If we get to the end, you know, I could always bump Rachel's song for doing a little bit of extra study. Okay, let's get to the outer planets. Now, what are you doing, Jenna? Stop that. The whole thing? Well, you can't talk to people. You need to be engaged in our discussion. All right, outer planets. Notice I didn't talk about the asteroid belt. That's that thing in the middle. There's a bunch of rocks in there that didn't quite get together. Why didn't they get together? Because Jupiter is really big. Jupiter is sometimes considered a failed star. If it was a little heavier, it would have lit up like a star, and we would have lived in what we call a dual system, where we would have two stars, just like on Star Wars. When Luke looks off into the binary sunset, and we would live on Tatooine, is what it would be. That's what I'm saying. Let's keep going. I got to keep going. I don't know who to ask anyway. What do you got?
Is there still a possibility that Jupiter could turn into a star?
No, because it's just not heavy enough. We will learn about stars next. Yeah, tomorrow. And gravity is pulling in on all of this gas, okay? And if there's enough pressure inside the center of these gaseous things, then what happens is hydrogen atoms get squeezed together to form two protons to form helium, all right? And when that happens, massive amounts of energy are given off, and that's when a star lights up, when that reaction happens. Doesn't have enough. I don't know how far off it is. I'm pretty sure I had to do that calculation once, but I don't have that, you know what I mean, at the top of my head. So no, we don't have to worry about, yes, so we don't have to worry about that. So we are out into what are called gas giants, and that's because they are made up of, well, more gas than rock. They do often have a center core that is rocky, but it would be so deep down in it, and the pressure would be so great that we couldn't actually get there. You can almost think of these guys as having like an atmosphere that's on like crazy steroids. That's like super thick atmosphere made up of crazy molecules like methane and all kinds of things that we don't have in our atmosphere. So if you were to take a rocket ship and fly through there, could you just fly right through the surface? I think you could, but then the pressure would become so great, kind of like if you go deep down in the ocean. You know how the pressure is great. If you've ever seen crazy movies about maybe a submarine that goes too deep and they're going to get crushed by the pressure of the water, that's what ultimately would happen. That spaceship would be just crushed by the pressure. You wouldn't actually be able to do it. The reason we don't call it the atmosphere is because we can see it. We can see the edge. Our atmosphere is transparent, so we don't consider the atmosphere as being the surface of the Earth because you can't see it. You just see the surface of the Earth, the rocky part. Here we can see it because they're made up of different colors, and therefore we simply call this the size of the planet, even though that surface is gaseous. Okay? All right. And again, I wanted to go through all this information, but it's okay. Great red spot right there. That's, by the way, it's getting smaller. In the last couple of years, this has been slowly dying down. Who knows why? Right? These are essentially storms, energy in that gaseous system, and this is like a giant hurricane that's been going on for, I don't know. Well, when Galileo looked at Jupiter in his telescope, he saw that big red spot, right? So in the end, it's been going on for a long time. I'm going to click ahead, and then I'll take questions. Rachel? You're right. Those numbers will be slightly off. I believe I have Saturn at 60, but I've recently read a report that they've found a bunch more around Saturn, and Saturn is now winning. Yeah. So is Saturn 62 at this point? And you're looking to get in on that deal?
Yes.
You've submitted names? Nice, good job. That's awesome. Yes. Is this going to be a 10-minute conversation? If it is, I might have to shut it down. What do you got? It moves around the surface because those bands have different orbital speeds, so they move past each other. You see what I'm saying? Yeah, so it does kind of move on the surface.
And so there's a bunch of moons, right?
There's a bunch of moons.
So did all of those happen from just hitting the planet?
No, our moon is the only one that's done that. The rest of the moons, they believe, formed just like the planets formed, except on a smaller scale. As the planet formed and things came in and the figure skater brought their arms in and things started to rotate, right? Then other little rocks that were in that space coalesced into moons, and then they went around. The Earth moon is special because it's just so pretty. No, the Earth moon is special because compared to the size of the planet, our moon is massive. A moon that big should never have naturally formed in the way in which I've been describing. That's why scientists believe something came in and knocked a chunk out of the Earth. Our moon is huge compared to all of the other planets that have moons. These moons are super tiny compared to that planet. So they formed like the planets did, except the planet was the central thing that caused that. You mean the red spot?
No, like on the Earth.
Yeah. Oh, yes, correct. Gravity is incredibly powerful in this case. Do we have the information about Saturn? Do we know that Saturn has lots of rings? Okay, awesome. Those are some failed moons, or some moons that ran into each other and then just smashed apart into the pieces, and then they just kind of kept rotating around that disk area. I want to move on to the next one because, again, time is good here. Yeah.
So you said the moons on Saturn have ice and rock. Does that mean those moons that smashed had life because it had ice on it, which is water?
That's a great question. You're now thinking.
I clicked on your link. I'm sorry.
It's okay. It's all right. You're now thinking like astronomers, and really, we now have. You can go in. It used to be if you took biology, you never even thought about astronomy because everything's here on Earth. But now we have bio, astro, whatever. And you're thinking like one of those people. Hey, if there's ice, could there have been water? And if there was water, could there be life? And those are good questions. Where did that ice come from? Was it a smashed comet, perhaps? Because you're going to read about comets being icy, et cetera, et cetera. Again, it's beyond my knowledge on that. But you're right. As soon as we think water, we can think life, question mark. You know what I mean? Yes?
Mine kind of ties in with that. If it wasn't for the lack of gravity on our moon, could the moon possibly
have created life? Well, you'd need water, right? And so, again, you're beyond my abilities. You're in the biology world, which is beyond my sphere of you know what I mean? That is. But biologists tell me, if there's liquid water and you got the right group of atoms in there that can do something, life things, then there's a chance. There's no atmosphere, right? Whether it doesn't have enough gravity to keep any atmosphere, because the molecules don't have to go nearly as fast. They can get out of that hole easily. So again, it's a good question. Could it have existed at some point? I doubt it. Again, I'm speculating at this point, right? And at this point, speculation, well, it might not be good for me. Okay. Uranus, that's the way people say it when they don't want to say Uranus. But that's just fun to say. Anyway, 7th. This one rotates in the opposite direction as well. So again, it spins in the wrong direction, and it's also tilted completely sideways. This was one of the main reasons I wanted to bring the axis tilt in. This is just about 90 degrees. So it does this, and it spins like that on its orbital rotation. So it's also been hit by something. Something, well, at least that's my theory. I don't know if that's the case, but something gave it a jolt to get it to turn sideways. Yeah.
Because circular, like how would you know in the first place what tilt is going and like how?
So my guess would be we are able to see enough features that we can see those features disappear on the backside here and come back around on this side. You see what I mean? That gives us a rotational direction. We must be able to see the features in order to know the rotation. You're right. We got to be able to see something moving on the surface. Yep. Yeah, you know what? Now that ring, I don't believe that ring is visible even with like a regular Earth telescope. I think you need to get like up close with like a satellite. Well, I guess it's not a satellite, but a spaceship. Not a spaceship. Not a spaceship. So it'd be great if we did. But you know what I mean? We send a probe to take a look. But you're right. Again, if it comes with the same idea as the gas rotation for the formation of planets, and then the rotation for the formation of the moons, if that's a failed moon, then that's indicating to us that its rotation is also sideways. So we could probably get that information from. It's not rotating. The rotation is also showing us that that plane of that disk. I really don't know. I don't know. I don't know where this picture came from. I didn't grab this one. Well, obviously, it's an alien. Yeah, it's an alien right there. That's the alien. Okay. All right, Neptune. You people, there's so many questions. All right, Neptune, 8th planet. It's blue because it had a lot of methane. That's it. No questions. What's that? What was I dressed up for Halloween? Oh, no, I was copper 2 sulfate. Okay. Let me finish off here. We got that? Again, orbital radius, that was a big fail. I thought we could discuss some numbers, but. All right. No, it's okay. Planet criteria. Hold on one second. Let's just go straight to this. So this previous slide here that I jumped ahead, that I'm going to click on it. Don't write it down. This talks about what it means to be a planet. You need to be in orbit around a star, like the sun. You need to have enough mass to be pulled into a stable sphere. In other words, you've got to be a spherical object, and that's what filled in the hole when the moon was formed. Gravity moved all the rocks to the valley, and the mountains came down and the valleys came up until it was a nice circle. That's what happens, right? The rocks fall down into the valleys, and we got that. I'm not sure about what they mean by this. Dominate its orbit. This is the important one. Mass must be greater than anything else that crosses it in the orbit. Now, I'm going to have you write this part down. Must dominate its orbit. What does that mean? You can look it up, but I think we know what it means to dominate, right? Like, you know, when you guys crush another hockey team, you've dominated, right? And so to dominate an orbit, I'm not sure what that means. I have an idea. What's that? To dominate, to be bigger and better than the other objects in the orbit? I think maybe that's a good way to think about it.
Enough mass that it owns
its own gravity pulls it into a roughly spheroidal shape. It must be.
Yeah, that's the circle. It's got to dominate its orbit. We're back to the dominating its orbit. Okay, let me tell you what I think this means. We used to, back when Pluto was a planet, back in the day when I was a kid, Pluto was a planet. Back when Pluto was a planet, and even when I was like a teenager, the order of the planets were wrong because Pluto's orbit is so ovally. Remember, they can be like an ellipse, right? Pluto's orbit is very elliptical and not very circular, that it dips in closer to the sun than Neptune does every so many hundred years. And for a period of time when I was a kid, Pluto was closer than Neptune. So the order was wrong. We used to say the order's wrong because I was a smart aleck kid too. That's not true. I was one of those guys, right? Just like a bunch of you guys in here, but I won't point them out. Anyway. I've offended a lot of you at this point. That's fun. Anyway, so I guess what they're saying is Neptune has that stable circular orbit. It's got kind of the real estate of that location where Pluto seems to just kind of be dipping in and coming out, and it doesn't really kind of dominate that orbit because Neptune is the one that's doing it. So that then put Pluto as a dwarf planet. And as we look out with better telescopes, we see all kinds of different things. To be honest, I don't care about these other names. You may have wrote them down. That's great if you did. But that's the logic behind it. We now know that we've got these other objects that we didn't talk about when I was a kid called dwarf planets that aren't really quite big enough to hang out with the big players, right? Does that make sense? Okay, all right. Now, that's my data table. I'm going to stop my video, and then I'm going to explain to you that you've now got some homework. You got to read a little bit about comets and about some other stuff like that. So I'm going to get that rolling. Once I get that done, hopefully the song can take how long? How long do you need? 1 minute and 53 seconds. Let me finish this. I'm going to escape here. And I didn't write anything on this, did I? Didn't write a thing. And I've got to stop this. Whoops.